Hello, today I'll be presenting on crystal oscillators. And essentially, crystal oscillators work by the piezoelectric effect, which arises from the unique properties of crystal oscillators that cause an electric charge to be generated when mechanical stress is applied to this crystal. And the reverse is also true. And when an electrical field is applied to the crystal, the materials themselves will generate stress and deform. And this reversible principle is how lighters create a spark, which we can see down here, and how some microphones record audio by registering the different beats in the air. So here we can see the regular piezoelectric effect when you apply stress and it creates a voltage here. And then over here you can see the reverse piezoelectric effect where you apply a voltage to a crystal and it creates a mechanical strain. The piezoelectric effect occurs because some crystals have a permanent electric polarization, in which the center of the positive charge is a tad offset from the center of the negative charge. Thus, when a piezoelectric crystal is compressed between electrodes, a potential difference occurs, proportional to the stress applied. And here we have a graphic where we can see they don't look very offset in the graphic, but when you apply a voltage and the crystal deforms, or when you deform the crystal and a voltage is generated, you can see that these charges here become a little bit moved out of place, which is, I think, pretty cool. So a crystal oscillator itself generates stable frequencies in electric circuit because of the piezoelectric effect. And so usually it's made out of quartz and it's placed between two plates that are electrodes, and an AC voltage is then applied parallel to the crystal. So when the crystal vibrates, it oscillates at a resonant frequency, kind of like an RLC circuit. So here's a very similar circuit that operates similar to the crystal. So what we observe in these parallel circuits is that when the series capacitor, which we see is right here, resonates with the inductor, the series inductor here, at the crystal's operating frequency, such that the impedance on this equivalent electrical circuit here, it creates a series frequency known as Fs of the crystal. And so here is an equation which gives you F of S. There's a second frequency that results when the inductor of series and the capacitance of series resonate with the capacitor of parallel as well. And that gives us F of P. And we can see how we can achieve F of P down here. And that also includes another thing called C of the capacitance of T, which is a separate equation. So the impedance against frequency is also creates a way for the crystal to exhibit three different modes of resonance, which is the capacitive, the inductive, and more capacitive. So what happens is that beyond a certain point, F of S, which we see here, the impedance of the crystal is minimized to be equal to resistant R, which we see here. So then the crystal behaves similarly to an inductor in this area until it reaches the point of F of P, or the parallel frequency. And then it starts acting like a capacitor again, and the impedance across the circuit is maximized. So you see that there's this relationship here. So this is kind of created what is called a parallel tuned tank circuit. We can also see how the resonance is affected over here. So essentially a crystal oscillator circuit needs to be tuned to either its series or its parallel frequency, because you can't have it be operated with both because they're very different. So the Q of a crystal oscillator is very important because it tells you its quality. And so when the inductance of a crystal is higher than its capacitive or resistive value, so it has a very high Q factor. Q is proportional to the frequency stability S of W of a tuned circuit, where d theta is the phase shift for a small change in nominal frequency F of R. So here are some equations that can be used to determine the frequency Q. So a lot of crystal oscillators are frequently used in many small circuits, and they're great because they have a very high frequency stability, so they're good in these circuits. They have a very high Q. They have a wide range of frequencies that are able to be manufactured. from kilohertz all the way to gigahertz. And I think the maximized one I saw was about 12 gigahertz. They're very long lasting, they're affordable, they're accessible, but they also have cons, which is that they're fragile and can't be used in low power circuits. Also, the frequency of oscillations cannot be substantially altered. They are also affected by temperature and radiation, and although they are difficult to stabilize in a circuit, there are ways to stabilize it. One man was explaining how you can, when you put a capacitor in series with a crystal, you will increase the frequency of the resonant circuit. So then the frequency of the circuit will go up. Now, if you'll go a bit above the frequency that you want. So if you want to bring it back down again, you can put the capacitor in parallel with the crystal, and that will decrease the resonant frequency of the circuit, which is a very handy way of creating the ideal frequency that you want. So two common types of crystal oscillators are the Colpitts oscillator and the transistor Pierce crystal oscillator, and you can see that there are some similarities because the transistor Pierce is a derivative of the Colpitts. And crystal oscillators are very cool, and so if you ever want to make one, you will have to probably get a lot of ceramic and compress it with a lot of compacting force. So the crystal's fundamental oscillation frequency, which is very important, of course, to the crystal, is determined by its size and shape when it is manufactured. So one corporation that creates these crystals says that the bulk piezoelectric components are made of one layer of piezoceramic material pressed with a lot of compacting force, and then these components are made by tape, casting very thin layers of piezoceramic material on which thin layers of electrode material are printed. And over 100 layers are then laminated. So it is a very complicated and very fascinating process. And that is all that I have today on crystal oscillators. I hope you enjoyed. Thank you.